Good night, everyone. To understand the basic semiconductor optical source things like LED and lasers, we first need the basic physics of PN junction. Because this is not night time, so I am unable to pronounce clearly. Okay, so please manage. We first need the basic physics of the PN junction because light emission originate from the electron hole pair recombination that this junction things. Okay, so in PN junction, in optical emission from the semiconductor. So in PN junction, first of all we have to understand the intrinsic semiconductor, a perfect semiconductor like pure silicon or the gallium arsenide with no impurities. Okay, the energy band structure, so valence band, conduction band, so they are separated by the band gap. Okay, eg at temperature above 0 Kelvin, some electron gain a thermal energy and jump from valence band to conduction band, and this leave a hole in the valence band, and this electron plus hole combine called carrier and responsible for the electrical conduction. Okay, and the formula for the one second. Uh, let's see. So what we are actually trying to say? We are actually trying in intrinsic semiconductor. In intrinsic semiconductor, intrinsic sic semiconductor. So in which it is a perfect semiconductor like pure silicon with a pure semiconductor and with no impurities. Okay, no impurities, and that is called intrinsic. So in which the energy band structure consists of energy band structure. So energy band structure consists what is valence band and conduction band. Okay, valence band filled with the electrons. Okay, and conduction band almost empty things. Okay, so these regions are separated by the band gap. Okay, so these regions are separated by the band gap and the above the 0 Kelvin. So above 0 Kelvin, above 0 Kelvin, some electron gain a thermal energy and jump from the valence to conduction band. Okay, valence to conduction band. Okay, and this leave a hole in the valence band. So this leave a holes in the holes in the holes in the valence band. Okay, and these hole and the electron pair is known as carrier. So electron plus hole is known as carrier. Okay, carrier and responsible for the electrical conduction. Okay, and the Fermi Dirac distribution. What is Fermi Dirac distribution? Okay, so Fermi Dirac distribution, a probability of electron occupy an energy level at temperature. So actually it is a probability. It's simply a probability of an electron occupying energy level E at temperature T. Okay, electron occupying an an energy level E at temperature T. Okay. So the probability formula is this one. We simply said probability of this one is equal to this one 1 by 1 plus exponential of E minus EF by KT. So how we write? So when we have to write, so simply P okay. So how that it's simply the probability is equal to 1 by 1 plus exponential of EF by KT. Uh, okay. So the probability formula for this one is this one. Okay, this is a valence band, and valence band simply consists. What valence band consists? Valence band consists is almost empty. So in this diagram we can see the valence band consists the electron and the conduction band is almost empty. But after at a temperature above 0 Kelvin, so above 0 Kelvin, the some electron gain a thermal energy and jump from the valence band to electron band or electron conduction band, and this leave a hole in the valence band, and this electron and hole pair is known as carrier. Okay, and the formula for this one is okay. So until we understand the Fermi direct distribution. Okay, so here EF is a Fermi level. Okay, K is Boltzmann constant. So in formula this one, where K is a Boltzmann constant, EF is a Fermi level. Okay, in intrinsic semiconductor, EF lies exactly in the middle of the band gap, and lies between the band gap. Okay, this indicates a small probability of electron in the conduction band. So small probability of conduction band. For the extrinsic, now we have to understand for the extensive intrinsic semiconductor. So to increase the carrier, impurities are added to. So in intrinsic semiconductor, so to increase the carrier impurities, so impurity or dopant are added. Okay, are added. Okay, so n type or p type. So in this example we can see synergy band for the n type semiconductor, p type semiconductor. So in n type, donor atom introduce energy level. The donor atom introduce the energy level just below the conduction band, and just below the conduction band donor atom represent donor atom introduce a energy level just below the conduction band, and electron easily jump from the conduction band to extra electron easily jump into the electron conduction band. Okay, so this made that electron can easily jump into the conduction band. Okay, and majority carrier is electron. So in this, and majority carrier is electron. Okay, Fermi level shift upward, the Fermi level shift upward, and the Fermi level little bit shift upward. Okay, closer to the conduction band. In p-type, the accepted impurities, okay, the electron introduce the electron and the acceptor atom introduce a level just above the valence. So acceptor impurities introduced just above the just above the valence band, okay. The electron from the valence band fill these electron and hole crater. So these electron go here and create a holes, okay. So Fermi level shift downward and closer to the valence band. In n-type semiconductor, we can see that the Fermi level go near to the conduction band. So we say that the donor atom introduce a Fermi level, energy level, and just below the conduction band, an electron can easily jump from the conduction band to a conduction band and extra electron. Okay, the majority carrier is electron, and the Fermi level shift upward closer to the conduction band. And the p-n junction. So in what happened? So pn when when p-type and n-type material, when p-type material and n-type material, okay. We have to select which color, blue, blue. Okay, what we have to do? This is a p-type material, in which p-type material in which we say. So as we see in the figure that the p contain all the holes and the n-type contain the electrons, okay. So electron from the n side, so electron in the n side and the diffuse with the p side, okay. So diffuse with p side, so hole from the p side diffuse to n side, okay. Holes from the p side diffuse with the n side, okay. And they recombine and leaving behind a fixed charge ion. So they recombine and leaving behind a fixed charge ion. So positive ion from the n side and the negative ion from the p side, okay. This region become a depletion region, okay. This region become a depletion region, okay. So electron in the n side and the electron from the n side diffuse the p side and holes from the p side diffuse with the n side. So they recombine and leaving behind a fixed charge ion, okay, for the positive ion on the n side, negative ion from the p side. This region become a depletion region. So no free carrier. There is no free carrier act as a insulating layer. There is no free carrier. They act as a insulating layer. Okay. So the potential barrier, what an electric field, the electric field that form which oppose the further diffusion. So what is potential? The electric field that form which oppose the further diffusion. Okay. When junction is in equilibrium, no external voltage. When junction in an equilibrium, no external voltage, no current flow, Fermi level become flat and across the junction. When the when the when the junction is in equilibrium, the Fermi level become flat, no voltage current occur. Okay. So this is a potential barrier. Potential barrier known as potential barrier is a electric field which oppose potential electric field which oppose the further diffusion. Okay. This one is Fermi level. This one like this one. Okay. After that we see the forward bias and forward bias in the p-n junction. So when a positive voltage is applied, when a positive voltage is applied as a p-n junction, forward bias means that applying the positive voltage as the p side, okay, with respect to the n negative, with respect to n side. So depletion, depletion with reduce. So this one, the size reduces, and the barrier height increases, barrier height decreases. Okay, the electron from the n side and the hole from the p side easily cross each other. Okay, when you forwarding, when you apply the positive current as from the p side, the depletion region become reduced and the barrier become reduced, and the electron from the n side and the holes from the p side combine easily, and they are called injected minority carrier. Okay, injected minority carrier. Okay, so how we explain? So forward biasing the p-n junction. Okay, so forward biasing in p-n junction, what we have to do? Simply say when positive voltage. So what when positive voltage is applied at voltage is applied at what, and the p side. Okay, okay. So effect is that effect. What is the effect? Effect, we can see that the depletion and depletion with reduce. Okay, reduce, and depletion with reduce, and the barrier height reduce, barrier height reduce. Okay, and electron from the p side, electron from the n side, and the holes from the p side crosses easily. Okay, crosses easily. Okay, you can say it crosses easily. Okay, and this is called, so this is called injected injected minority carrier. Okay, okay. This result in the current flow more this result in the current flow, motion, electron and hole recombine and release energy, and electron plus hole recombine and release energy, release release okay, release the energy. Okay, in suitable. Okay, let's see. So, so what happened? So after doing this in the forward biasing PN junction, a current flow, electron in the combined energy release energy and suitable for the semiconductor diode band gap, and this release a photon. So, so what happened? Suitable for the semiconductor and diode band gap, or suitable for the diode band gap. Okay, band gap and energy released. Okay, released and released which as a photons. Okay, and this is the basic. So this is the basic of LEDs and the laser diodes. Okay, this is basic for the laser diode. So why PN junction is essential for the optical emission? The forward biasing inject the excess electron and holes into the opposite region. Recombination happen near the junction, and for the diode band gap material, recombination is a radiative photon emission, and the photon from the light of LED and stimulated emission or the stimulation for the laser. Okay, so we have studied the intrinsic semiconductor Fermi level things. Okay, so intrinsic means a pure semiconductor with the equal number of electron and equal number of holes. Fermi level, it indicate the probability of energy state occupancy. Okay, n type what we call n type. So n type so n type is a n type the donor impaired extra electron. Okay, so in which EF move up. Okay, in which EF move up, the Fermi level moves up, and the in p type the Fermi move down. Okay, p-n junction interface between p-n junction depletion region, no mobile carrier from the electron forward ice मतलब reduced barrier injected carrier across this one. The combination electron plus hole energy releases spontaneous emission. So let's understand the spontaneous emission. So actually, when PN junction in the forward bias, when PN junction in the PN junction forward bias, electron and hole pair are pushed across the junction. This cause a large number of minority carrier to injected into the opposite side. Okay. So what we said. Okay. So in PN junction. Okay. This is P and this is N junction. Okay, when forward bias is electron and hole pair push each other, this cause a large number of minority carrier to injected into the opposite region. Okay, this excess carrier injection lead to the recombination. The excess carrier injection lead to the recombination and the light emitted if semiconductor is in the diode band gap. Okay, and the light emitted if the semiconductor in the diode band gap. Okay, the material like GAS. Okay, this emitted light is called spontaneous emission. Okay, so what happened when what happened in the forward bias things when so in the p side electron move from the n side to p side. Okay, and the holes move from the p side to n side, and the injected carrier recombine at the junction. The injected carrier recombine at the junction. Okay, and as we suitable in 6.11 we can see that we can see uh, we can see and the holes are moving toward the n side, and the electron are moving toward the p side. Okay, the recombination process in the p region, the conduction band in the p region, the conduction band normally contain few electrons. Okay, conduction contain few electrons. Okay, but in forward bias injected electron filled some of these empty seat. Okay, similarly in the n region the injected hole fills some valence empty state. So the both side junction suddenly have an electron in conduction band, holes in the valence band. Okay, when an electron drop from the conduction band to valence band, the energy is released. When the electron drop from the conduction band to valence band, the energy released is approximately equal to the band gap. So there is two possibility. There is two possibilities. Okay. So there is two possibilities. One is radiative or non-radiative recombination. Okay. So when the energy is equal to band gap, there is two possibilities: radiative, and radiative versus non-radiative recombination. Okay. Radiative recombination: if a semiconductor is a direct band gap material, the electron fall directly from the band gap. When electron fall from the directly from the band gap, the proton is emitted and useful for the LED and laser. Okay. Thus the photon energy is termed as Eg is equal to h nu S lambda. When since E is equal to Eg, so wavelength become 1.2 by Eg. So this is the key equation for LED wavelength. So LED wavelength is equal to 1.24 by Eg. Okay. For the non-radiative recombination is equal to radius in the indirect band gap. Okay, like this one, the most recombination become lattice vibration. Okay, this produce heat, not the light. Okay, non-radiative, this produce heat, not light. So this is why silicon cannot use as a LED use for the LED or laser device. So that's why the silicon is not used for the LED in this one. Now we have to see the definition of electroluminescence. So electroluminescence is a light emission due to the light uh, light emission due to the electrical excitation. Okay, where is the light generated? So nearly the junction are the most recommend. Okay, the combination try. So this is where is the light generated? Nearly at the junction where the most of the recombination thing are, but the carrier also diffuse away and recombine anywhere. Recombine, thus the emission area is spread over the small region across the junction. Mm, okay. After that, we have to understand the direct and indirect semiconductor. So we will do in next lecture.